morning. So a few years ago, I was gifted from an outgoing colleague their Astrodynamics and Orbital Mechanics lecture course, and it was a delight. So astrodynamics is a fundamentally four-dimensional problem, and up until a few years ago, it was taught by fundamentally a two-dimensional approach. So this works. 50 years ago, I think we can all agree that these folks did okay for their simple two-dimensional chalk and talk approach to astrodynamics training. But I don't know about you, but there have been times when I've looked out into the dimly lit lecture room after I've been chalking some Newton's laws and some gravitational flyby calculations and seen something a little bit like that. Just because we did it like that for decades doesn't mean to say that there aren't ways of improving. And courtesy of modern technology, there are lots of ways of improving this and really changing the way that students engage with a challenging subject like astrodynamics and giving them some opportunity to really learn actively. There are a few tools around. The most well-known is called Systems Toolkit from AGI. It's a fabulous piece of software with a fabulous price tag to match. And they have, in olden times, the software was essentially free for educational use. But they've really started to tighten up on that now. Having wrestled with their licensing arrangements for a few years, I came across this tool. So this is the General Mission Analysis tool, and it's a project that's coordinated by NASA, but it's an open source project. It involves industry as well as NASA. And it looks suspiciously familiar to anybody who has some kind of exposure to STK. I suspect that's not an accident. And just like STK, it's validated. And for me, when I'm teaching astrodynamics or any kind of professional skill, it's really important that students understand the value of validation. The fact that this is software, yes, but it's tested against real world, real mission operations. And so in the last few years, STK has been adopted, GMAT has been adopted by NASA to support a number of missions. And we talk a lot about that during the opening sessions of the workshops that I give. It's got extensive interfaces to external coding, and importantly, it's free. You can get it for Windows. It now works very well on Mac and Linux. It's lots of documentation, lots of tutorials. And there is a user forum. I find the forum is a little bit variable in its usefulness, but it does exist. So I don't have a lot of time, so I just want to highlight a few basic properties of GMAT before we look at a few examples of how we use it at Leicester. So the first point to make is that it's got a lot of extensible system interfaces, and that means that you don't have to constrain your work to the environment within GMAT. And in fact, that's really important because while GMAT and tools like STK provide really nice eye candy, they provide useful visualization that can help students appreciate the concepts, you don't necessarily want to do all of your analysis within that system. And in fact, it's not practical. Some of the analysis that you might want to do involves some significant levels of computation, and you need to be able to break out. So you can use MATLAB, Python, you can generate plugins as well. There are also extensible model subsystems. What does that mean? Well, GMAT incorporates models for atmospheres, for different gravitational parameters, for different kinds of calculation to solve mechanics problems. So in principle, you can add different models, different atmospheric models or gravitational models or so on into the system. I toyed with the idea of doing some practical demonstrations up here and rapidly decided that probably wasn't the way to go because things will inevitably go wrong. So I'm just going to show you a few screenshots. So this is the the basic interface view, and you can see that if you've seen STK before, it looks very similar. So there's a resources column on the left-hand side in which you define your spacecraft, your gravitating bodies, which you select atmosphere models and so on. And then you've got 3D and 2D windows, so you can look at the orbit or the trajectory in the reference frame of whichever object in the solar system you're interested in, and you can look at ground tracks, and you can define more of these windows as necessary. You can define new coordinate systems. For example, if you wanted to define some coordinate system that was the Earth-Jupiter barycenter for whatever reason, you can define that, and you can plot your outputs in that window. So at Leicester, we use this in a number of areas. We have a third-year Astrodynamics skills elective, but I also run our MSc Astrodynamics module using something based around this workshop. I won't go into that in detail. We can talk about it in the afternoon sessions if necessary. So this is really how I introduce my students to the system. So once we've gone through some basic introductions to fundamental orbital dynamics, so things like the trajectory equation, the energy equation, the relationships between semi-major axis, semi-minor axis, and eccentricity, we can use GMAT to compare calculations with model outputs. So we can build a very simple restricted two-body Keplerian problem. We can get the students to calculate various parameters, and we can then model that in GMAT. So just conveniently behind the coffee dispenser, there's a model, a view of that scenario, and a whole set of numerical parameters which come out of this, which you can use for time variable or static analysis, and they can compare the results and experiment with that system. Okay, so again, I've put some content in here which we might talk about around the table this afternoon if necessary. So this is a student example from one of my workshops, and this is looking at the J2 perturbation, calculating the inclination and altitude for a specific kind of sun-synchronous orbit. So in this lighting it might be difficult to see, but this is the Earth-Sun vector. This is a rather large satellite, it seems, in orbit around the Earth. And what you can see from the eye candy generally is that orbital plane is tracking the Earth-Sun line. But a 3D window isn't necessarily the best way to show that. So the students use the extensible interfaces, and they use data from GMAT to plot something a little bit more meaningful. So in this case, for example, we've got the right ascension of the sun as the solid line, and we've got a non-sun synchronous orbit and a sun synchronous orbit. So they can test their application of things like the rate of change of the right ascension, the ascending node, and establish the relationship between inclination, orbital radius, and the sun synchronous condition. So J2 is one of the perturbations. Here's another very important perturbation. So this is EastWest Drift. And in GMAT, what we could do is switch between coordinate systems. So we can now switch into a planetidetic coordinate system. We can set initial conditions that describe the position of 4 geostationary satellites around the Earth. 2 of these exist at the stable equilibrium points, and 2 of them exist at the unstable equilibrium points. Students tend to spend hours trying to set these up and failing because they set them up in Earth-centered inertial coordinates. And as soon as you show them planetidetic coordinates, it becomes much simpler. So you can do it within a minute. And if I run this again, so hopefully you can see, so I have 4 satellites up here, and 2 of these satellites remain fixed with respect to the geographic features below, and 2 of them start to drift. And this gets us into discussions about station keeping, about mission lifetime, constraints imposed by the need to burn fuel to keep your satellite on station, concepts like graveyard orbits. So that simple demonstration, which we can set up within a few minutes leads on to a whole set of discussions and exploration of how you actually do your maneuvers. What are the requirements on the propulsion system for keeping a satellite in station if it's not at one of those equilibrium points. So we also have atmospheric models. For example, we have introduced an atmosphere. And so GMAT has a number of standard atmospheric models, so I'm using M-size 90 here. And within that model, so you can see this is the definition window in the bottom, might be difficult to see from the back. But as well as defining the atmospheric model, we can define specific elements of the space weather conditions. So we can set the solar flux, we can set the geomagnetic index. We do use this in courses on space weather and space plasma physics. So we can also use GMAT to support those examples. I'm not going to try rerunning that because bad things will happen. But the outputs that you get from GMAT can help students to understand for orbits that are very low altitude and encounter significant amounts of atmospheric drag. You can see the effect on the spacecraft orbit lifetime. This is without an atmosphere included in the model. This is two identical satellites operating in slightly different solar states within the M-size 90 model, and you can see that there's a difference in the orbital decay characteristics. And because GMAT also includes physical parameters for the spacecraft, such as the coefficient of drag or the coefficient of reflectivity, if we want to incorporate the effects of, say, solar radiation pressure, it's an enormous kind of playground for testing out ideas relating to spacecraft system design, looking at the effects of, say, spacecraft having large solar arrays versus spacecraft with alternative power systems and what effect that has on the mission. So we go beyond the Earth. So this is some work that we did on, this is from a student piece of work, where we sent a small swarm of spacecraft from the Earth to Jupiter. And the spacecraft were identical apart from having some very small differences in the initial conditions that were used for that orbit. And what you can see, let's run that again, slightly nervous about doing that. What you can see is that the spacecraft, when they encounter Jupiter, they're all together, but as soon as they start to feel Jupiter's gravitational field, they disperse. And that's all very nice and pretty. But the point is that we teach the physics of gravitational encounters. There are some very important relationships, for example, relationships between the eccentricity, the arrival velocity, the radius of periapsis, and the mass of the planet. This is the relationship between the turning angle and the eccentricity. So these are fundamental parameters that are used when you want to plan an interplanetary mission using multiple gravity assists. And so the students can use this system to test their model outputs, experimental if you like, against the kind of predictions that you get from theory. This is something that we call the synchro pair, because I'm a bit of a Red Arrows fan and I had to find a way of getting that in. So these are two identical spacecraft, but they encounter the planet in identical orbits, except that one comes from the trailing hemisphere and one through the leading hemisphere. And what you see there is that you get a change in your heliocentric energy. And this is the basic principle of using gravitational assists to modify spacecraft trajectories. So there's a whole lot of learning that takes place after that, after you've actually done the graphical work and understood the application of those processes. Now, one thing I should say is that GMAT is not good for planning gravitational assist trajectories. Okay? For this kind of work, you need Monte Carlo simulations, and GMAT just isn't set up for that kind of thing. You can do this in STK, but even STK isn't the ideal environment. So we use different codes. So we use PICAP and PIGMO. So these are ESA tools. so PICAP is a Python implementation of a Keplerian orbital mechanics toolbox. PIGMO is actually non-specific to orbital mechanics, but it's a set of nonlinear optimization codes. And by combining those two things together, you can do some really great work on calculating gravity assist initial parameters, beneficial encounters, and so on. And one of the easy gets from PICAP and PIGMO is the ability to produce things like this. So these are pork chop plots. We can use these to identify launch windows constrained by the energetics of the launch vehicle, for example. We can output right ascension and declination of launch asymptotes, and we can use those as initial starting conditions in GMAT. So PICAP and PIGMO provide us with inputs to GMAT, which can then be used to model gravity assist encounters. So this is some work done by my PhD student, Sam Frampton, with apologies to Lucy, because we stole Sam from Lucy, sorry about that. But he's really good, which is why we stole him. So these are gravity assist trajectories looking at encounters with Uranus. So these are many thousands of gravity assist attempts, some of which prove to be very beneficial. And so we can use PIGMO and PICAP to identify the most beneficial of those trajectories, and then extract the parameters to understand what the starting conditions and what the parameters at each gravity encounter are, leading to those. To finish. So I'll just finish with the final mission challenge. So we go through a set of sort of directed explorations in GMAT, but at the very end I give them a little Christmas present. So I give them a final challenge, and I essentially say, this is what you're going to model. Now go away over Christmas, don't even think about emailing me, and come back and show us how you've achieved this particular challenge. So last year I wanted them to analyze the Type H hybrid Apollo lunar trajectory. So these are the trajectories which departed from free return and then allowed the Apollo program to access different regions of the moon. So that's exactly what they did. Several groups got the full solution, including correct splashdown dates. The way that we do this is you can use GMAT to present your work. You can use outputs of numerical models. You may not use PowerPoint, as I'm doing here. You may not use the gift of interpretive dance, because when you take away PowerPoint, students then start to kind of do this kind of thing, and that's no good either. We use an approach which is adopted in the ESA concurrent design facility. Okay, if you're going to present something, don't waste your hours presenting a PowerPoint presentation, like I'm doing. Use the model itself, which means that when you get to the end of your presentation and you get to the Q&A, if somebody says, what would have happened if you did this, or have you checked that? You just go to the model and you rerun it and you say, okay, let's have a look and see what happens. And that's what they do. And this is a real challenge for them. They don't like this to begin with, but by the end of that session, they really embrace it, because it turns into a really active discussion. So I think this has worked out very well. So behind GMAT, GMAT's visual interface is a full scripting language, and very often to really get the details, to get access to the best approaches, we get the students to release their grip on the nice GUI interface and start looking at the scripting, and you can do optimization work in scripting very well. So this is a typical mission sequence where we have a series of stages: Earth launch, arrival at the moon, circularization, descending to the surface, departure from the moon, trans-Earth injection, arrival at the Earth in the right part of the right ocean at the right time. And not all students got it, but a number did. So I don't think these are going to work. Okay, so a little bit quick, but this is the hybrid trajectory. So you can see that they've succeeded in launching from the Earth to the moon. They're in orbit around the moon. then a trans-earth injection, which leads them back to the Earth, splashing down at the right point in the right ocean. I was quite impressed. I didn't expect them to get that level of agreement, but they did. And they go away and they invest an awful lot of time doing research. The information that we have is that students actually like this. They go away and they're talking over Christmas and playing with the different approaches. Okay, I think I've overrun my time. So, takeaway points: it's open source, it's free, it's validated, it works. It's not perfect, but it is really an excellent basis for a very interactive, engaging Astrodynamics module. We've really used this now as an integral component, not just of the taught modules, but of student projects as well. You can use black, grey, or white box implementation, so you can reveal as much of the fundamental physics as you want. So I can also use this for early stage secondary school demos, but without revealing as much of the detail. It's extendable, and there's lots of documentation. And if you want to find out more, we published this in the Journal of Learning and Teaching in Higher Education, so you can find the link online. And there's a few resources there which you can get in the presentation file, which I think, are these going to be available after the session? So there's a few links there with some ideas for ways of attempting initial condition calculations, as well as the GMAT itself. So that was rather rapid, but I hope that's useful. And obviously this afternoon I'm happy to go through and give some demonstrations, which I shied away from doing in the talk part. So, okay, thanks a lot.